name is Nitin Srinivas, and in this video I am going to explain the design of a two-stage OPAMP with Miller compensation and the design of an LDO. So first, let us look at the design of a two-stage OPAMP with Miller compensation. So this is the two-stage OPAMP design. The first stage consists of a differential amplifier with an active load, and the second stage is a common source amplifier. So I assume the slew rate of this OPAMP to be 30 volt per microsecond, and I took the value of Miller capacitance as 2 picofarad. So from these values I can find the slew rate is equal to the current through the MOSFET, the tail current through the MOSFET by the Miller capacitance. So as this is 2 pico and the slew rate I chose is 30 volt per microsecond, the tail current I got is around 60 microampere. So the tail currents of these both MOSFETs is 60 microampere. So now I need to figure out the W by L's of all these MOSFETs. For figuring out the W by L's, I fix the VG, VGS and the VDS and the IDS of the MOSFET, and then I found out the W by L by fixing all those three parameters. So let us see how I decided the W by L for each MOSFET. For the NMOSes, this is the circuit I used to fix the W by L, and for the I'm going to simulate each of the circuit and fix the W by L. So first I'm going to launch the ADEL. I already stored all the states. So in this, for the tail MOSFET, so this is the simulation parameters for the tail MOSFET. By tail MOSFET I mean this MOSFET. Other thing is, I assume the voltage here 1.8 volt and the drop here to be 0.9 volts. So the voltage here is around 0.9 volts, and here the voltage I assume is 0.45 volt. So for this MOSFET, the drain voltage is 0.45 volt, and I also assume the MOSFET's threshold voltage to be 500 millivolt, and I assume that the overdrive voltage of each MOSFET should be around 100 millivolt. So this VG should be around 600 millivolt. That is what I took here. So the VG is 600 millivolt and VS is 0, so VGS is 600 millivolt and VTH is around 500 millivolt. So the overdrive voltage is around 100 millivolt and the VD is 450 millivolt. And when I simulate it, this is the plot which I get, and from this I know that the current through the MOSFET should be 60 microampere. So you can see that around 9U the current is around 60 microampere. By 9U I mean the W is 9U and the length of all the MOSFETs are fixed to be at 400 nanometers. So in this case the W is 9 micrometer and the length is 400 nanometer. From now on, let us assume that the length of all the MOSFETs is fixed at 400 nanometer. So all these values correspond to only the width of the MOSFETs. So from this, we got the W of this MOSFET and this MOSFET, which is fixed to be 9 micrometer. Now let us see the W of these two MOSFETs. So here the VD is 0.9 and this voltage is 0.45, and according to that the current through this MOSFET is 30 microampere because the current equally divides in both the MOSFETs. So from these conditions we have to find the W by L of this MOSFET, and for this VP also I assume 1.05. Again the condition is I took the overdrive voltage to be around 100 millivolt. Let us see the W by L of that MOSFET. So for that I need to load another ADEL. So in this I want the current to be 30 microampere. So from the graph we can see that around 19 micrometer, the current is 30 microampere. So from this graph, I fix the W of both the input MOSFETs to be around 19 micrometer. And the next is the W of this MOSFET. We want the current in this part of the circuit, that is the common source, to be around 5 times the current in this. We need to have that condition such that the slew rate of the OPAMP is internalized, that is, it doesn't not depend on the output load. So for the third MOSFET, I need to load another ADL. So in this case, the VD is 900 millivolt because I assume this voltage to be 0.9 volt and this to be 1.8 volt. And the VG is same as this MOSFET, and that is 600 millivolt, and the source is grounded. So if I simulate it, and the current through this is around 300 microamperes, that is 60 into 5. So for around 300 microampere, the W of the MOSFET is around 30 micro. So from this, I fix the W of this MOSFET to be 30 micrometer. So now all the NMOS's W's are fixed. Now let us look at the PMOS's. For the PMOS, this is the circuit I used to find out the W. Now let us launch the ADEL. So for the PMOS present in the differential amplifier, these are the values. Let us look at how we got these values. The VD is 900 millivolt, that is, this node is 900 millivolt, 0.9 volt, and this is the source, and it is fixed at 1.8 volt. And the gate is also connected to the drain, and both are at 900 millivolt. And the current through this PMOS is 30 microampere, which is the same as the current through the input MOSFETs, input NMOS. So now running this, so from this you can see that the current of 30 microampere is around 2.1 micrometer. Is the current of 30 microampere will get at around 2.1 micrometer of the width. Even for the PMOS, I fixed the length to be 400 nanometer. So the both PMOS's W are fixed through this. So these both are around 2.1 micrometer. Let us look at this PMOS. For that PMOS, I am loading the other state. So for this PMOS, the current should be around 300 microampere. Yeah, this is the plot, and we get 300 microampere around 20 U. So from this, the size of this PMOS is fixed to be around 20 micrometer. So here all the NMOSes and PMOSes are fixed. I slightly adjusted the input MOSFET W because the threshold voltage I assumed is 500 millivolt, but in reality, due to second order effects and several effects, the threshold voltage is not fixed. I observed that the threshold voltage of this is around 500 millivolt, but this MOSFET's threshold voltage is around 630 millivolt. Because of this, there are some deviations from the expected values, and to account it for that, I kept the value of this WN as 15 mu. From the graphs, I got it as around 19 micro. So let us try to simulate the circuit. Okay, first let us see in what regions all the MOSFETs are operating in, because that is very important. So in this, to see in what regions they are operating in, I'll go to annotations, DC operating points, and then setup. I'll add region here. So you can see that all the MOSFETs are in saturation, and that is what we want. And also you can see that the current of 60 microampere is equally dividing between both the MOSFETs. And let us look at the stability of this circuit. So this is the loop gain of the MOSFET, and this is obtained using stability analysis. So we can see that the gain of the MOSFET at DC is around 62 decibels. And we can see the stability of this MOSFET through stability summary. So we can see that the phase margin of this MOSFET of this OPAMP is 62 degrees, which is a good number. You can also see the phase margin through the graph, to the Bode plots. So phase margin, to find out the phase margin, we have to find out where the plot reaches 0 dB. So this is dB, and so we can see that at around 0 dB the phase is around 62 degrees. So from this we can say the phase margin is around 62 degrees. So we can use either the stability summary or the Bode plot to analyze the phase margin of the circuit. And now I'm going to use this OPAMP to build an LDO. And one more thing that we can observe in this OPAMP is that initially we assume the voltage here to be 0.9 volt, the voltage here to be 0.45 volt, and the current through this to be 60 micro, and the current through this to be 300 micro. So we can see that all the values are almost close. There is a deviation because we didn't consider the second or higher order effects while simulating for the MOSFETs, and each of them we considered individually. So when we put all of them together, there are going to be some effects which slightly change the value of this assumed values. So this is the LDO circuit. In the LDO, this two-stage OPAMP is used as an error amplifier. So this is the pass transistor, and these are the resistors which are used to provide feedback to the circuit. So LDO stands for low dropout voltage regulator, and low dropout is there to signify that the power efficiency of a voltage regulator will increase when the dropout is low. So having a low dropout corresponds to higher power efficiency. And in this circuit I designed it for VDD of 1.8 volt and an output of 1.2 volt. So let us simulate the circuit and see. Yeah, this is it. First, let us look at it at the DC operating points. So yeah, from this we can see that the voltage at the output is 1.2 volt. Also, to check the DC operating points, these are the DC operating points, and again to view the annotations of regions we have to do the same thing. Okay, so again here also we can see that all the MOSFETs are in saturation, and to decide the values of this RF, these two resistors, what we have to do is, because this circuit is in negative feedback, the voltage at this node must be equal to the voltage at this node, that is Vref. This Vref is produced by a reference circuit like band gap reference circuit. So in our case, this Vref is around 1.05 volt. So that means the VO into R1 by R1 plus R0 must be equal to Vref. So from that equation we can find out the value of RF by R1, and from that ratio we can choose the value of RF and R1, and also based on the power consumption values and all, we can choose in what order we want the value of resistors to be. If you want lower power consumption and all, we use higher value of resistances. And this is the load that is used to simulate the LDO. So and also regarding the Miller capacitance, the Miller capacitance ensures that the second pole of the system is outside of the gain bandwidth of the system. So it helps in pole splitting, which ensures that we get a proper phase margin. And for this circuit, let us see the line and load regulation. First we'll see the line regulation. In the line regulation, I am varying the supply from 1.6 to 2 volt and seeing how the output is varying. So let us run it. So we can see that the output is varying by 0.1 millivolt, which is a very low value, and the supply is varying from 1.6 here to 2 here, but the maximum variation is around 0.1 millivolt. Now let us see the load regulation. In the load regulation, I am varying this current from 10 microampere to 1 milliampere. So again here also we can see that the variation is very low. At 10 microampere the voltage is this much, and at 1 milliampere the voltage is this much. The variation is around 0.3 millivolt, which is again a good value. Now we'll see both the load and line regulation together, and also these load and line regulations are static because there is no transient part in them. So so in this, to see both the load and line regulation together, I'm going to use parametric analysis, in which I'm going to add VDD, and I'm going to vary it from 1.6 to 2 volt with a step of 0.1. Because in the DC I am already varying the current. Both together will give us the load plus line regulation. Yeah. So here also we can see that the minimum value is around this and the maximum is around this value. So again here also we can see that the variation is around 0.4 millivolt, which is good. So these plots correspond to these values of VDD, and the load is varying here, so it has both line and load regulation in the same plot. And also let us analyze how the feedback is working in this circuit. For example, assume that this voltage at this node rises. As this is a PMOS, this node will go down. If this goes down, this node will go down, and as this goes down, this node will increase, because this we can think of as a common source amplifier. So if this goes down, this will increase. If this increases, this is a PMOS, so again this decreases. So initially we increase this, and the feedback is causing this to decrease. So we can see that the concept of negative feedback is there in action. So, and that's it. Thank you. The next part, I'm going to explain a slightly different way of designing the two-stage OPAMP. To explain the design of a two-stage OPAMP with Miller compensation. So this is the circuit for the two-stage OPAMP. It has 5 NMOS and 3 PMOS. This is the first stage, which is a differential amplifier with an active load, and the second stage is a common source amplifier. So for the design of the circuit, first we'll choose a Miller capacitance, and generally it's taken around 1 to 2 picofarad. I choose a value of around 2 picofarad, and then we have to choose the second stage current to first stage current ratio around 5 to 10 times. And from the slew rate specification of the OPAMP, we can find the first stage current, because the slew rate is given by the current through the MOSFET M5 by the Miller capacitance Cc. And from the gain bandwidth specification, we can find GMN1 as gain bandwidth is equal to GMN1 by the Miller capacitance. And from the early voltage and current, we can determine the output resistance of all the transistors. And from the value of the DC gain, we can find the value of the W by L ratio of the MOSFET M3 and M4. So the calculations of all these equations are written in MATLAB. This is the code for it, and I choose the appropriate specifications for the OPAMP. From this specifications I got the value of W by L, and I simulated the circuit using ngSpice. Circuit using ngSpice. This is the code in ngSpice, and these are the plots obtained by it. So we can see that the gain is very high. It's around 60 decibels, and we can also see that the phase margin is very good, because at 0 dB gain we have a phase of around minus 100 degrees. That corresponds to a phase margin of around 80 degrees, which is a very good phase margin for an OPAMP.